Good evening. Welcome to today's class. Today we will be talking about what are the examples of small signal analysis. In the previous class, we stopped off at understanding what is DC analysis and how do you perform a small signal analysis. We will now continue from there. So the first point is, how do you complete a DC analysis? Like in 2 classes back, we understood how do we do a analysis. The first thing we do is we will understand, given the circuit experiment or what is the circuit given, we will begin. First, we will start off and give a mode of operation, and then we will enforce and see what is the response that is seen. So after the response is done, you will do the analysis and you will check if your assumption is right or wrong. Next, what you will do is, after you get the check, now you have defined what is the DC operating point. You know what is a DCOP, and from there on, you will use 2 very important factors. One, if you have a voltage source, right? Now this voltage source, when you turn off a voltage source, it becomes a short circuit. Fourth, if you have a current source and you turn it off, you have an open circuit. Fifth, in small signal amplifiers, you will typically use a capacitance, right? And in capacitance, you will understand that in DC condition, the impedance of a capacitance is infinity, so you will get an open circuit, right? Now, what are the advantages or learnings that you have? A voltage source will always have a small resistance in series. What about the open circuit? In a current source will have a large resistance in parallel, right? And a DC circuit during open condition is a large impedance, right? So these are the 3 conditions that we will regularly use in any small signal analysis. Note that this is defined for DC signals only, or DC time only. So, how do you proceed further? So now we will understand now what is the goal of this DC analysis. The goal of the DC analysis is as follows. 1, find the DC voltages VGS, VDS of the transistor. You already know what VT is. VT is defined already. Important thing is, you do not need to find out ID and GM in the beginning. These are only going to be the next step. So these 3 are your DC analysis. Next one is where a critical one. What is this critical step? Next is a critical step wherein you will replace transistor or a MOSFET you will replace a transistor or a MOSFET with its small signal equivalent. Small signal equivalent. Now, note this is the one which can trouble you. But if you get this right, analog design is simple and it becomes very easy. So this is the critical phase that you will have to understand, right? What are the things needed? Replacing MOS with small signal equivalent. Now this is the next step. What happens when you replace? First of all, you need to understand there is always a human element here. How good is your fundamental? That fast is going to be the response in which you will be able to draw the circuit, right? Remember, it is a very simple step and it is also very straightforward. If you follow the simple rules, it requires very few. Now there are 4 rules that you have to follow. These called be your 4P, or like how some people have written before. Remember, these are your 4P. This is how I have generally written and to replace. First thing, patience. You need to be patient and do it with precision. Never make a mistake if you follow the same thing. Reason is, the moment you have patience and precision, it will help you to be persistent. And with persistence, you will always ensure that you have a professional approach, and professionalism will come in depth automatically. This ensures happiness. In the first time, you don't have to repeat anything if things goes correctly. Technically, what do you have to follow? You have to follow only one important step here. Find out what is the GM. This is a crucial. Always remember 2K times VGS minus VT. Another one that you will need is R0, which will give you 1 over lambda K VGS minus VT the whole square, or 1 over lambda ID. These two, if you have, in most of the cases, it will be extremely simple and done. In other places, look, why I say most of the places, along with these, you need to have understanding of what is a voltage source, a current source, right? How do we define a voltage source? We will define a voltage source like this. We will define a current source as follows. Voltage source, current source, and then you will have the capacitance. Most of the places you have. For sake of completeness, there are times where you will need the inductance, and in this case, inductance in a DC state, it is a short, right? And in a DC state, the capacitance is open, right? Next, in a DC state, current, when you turn it off, is open, right? And voltage source, when it is open, it is short. So remember, this is the voltage sources and the passives that are present. Apply them carefully. Find out GM, find out R0, apply them carefully. Another block which will come as it is without disturbing you at any time is your resistor. Wherever your resistor comes, you will just follow its methodology. You don't have to disturb anything, and resistor is always going to be aiding your work because it will not transform itself in any way, whether it is DC or AC. It just stays. So that is your best friend in many cases. Now comes the important part. We will now look what happens in this device. Understand that your transistor is a 3-terminal device. I will redraw the 3-terminal device as follows. We said on the right side is your gate. Top side typically will be your drain. Bottom side is your source. So how do you connect it? For an NMOS device, this is how it will look. Now, what are the other equations that we had said? IG is 0. ID will flow out through IS. Observe the notations. Both are always small, right? Now, what is VGS? This is VGS. DC plus AC. This is VDS, DC plus AC. Here you will have the currents, both DC plus AC. I am writing this explicitly so that it will be useful for us when you have to identify. This is clear. Now, how do we convert this small signal model? The small signal model is to be converted same way. Your gate is here, source is here, drain is here. If you remember, we said there is going to be a source is common. So this will be the negative terminal for both, or the common terminal in both conditions. So this will be your plus minus. So this is VGS. This is your VDS. Now, we know that VGS times something gives your current flow. You remember, voltage controlled current source. So this is your voltage control. You'll have to draw a current source, which is your dependent source. Dependent source are drawn with a rhombus, current in the same direction. So this is your current here, given as GM VGS. Then there is the output load connected across the DNS, and this is called as R0. Remember, in the previous slide, we said we need GM and R0. So this is the reason we need both GM and R0. Let us fill up the rest. IG is equal to 0. This is your ID value. Same is your ID value. This is what is the same. Now, what all do you observe here? The transistor is a MOS, 3-terminal device only. In our analysis, we have not included the bulk. So we will concentrate on voltage gain source. The behavioristics that we have, let us summarize. Blue and red. What do we need? We need VGS, we need VDS, we need ID. So these are the 3 things that you need here. Now, what do these get converted into? These get converted into GM and R0. If you see, these are your inputs. Inputs will be VGS, VDS, ID, GM, R0 will be your output. Right? Hope you got that. Therefore, whatever is within this gray box is same. So this is the equivalent expression, and this is for common source CMOS configuration. You will use this as the same. Now, whatever happens, if you want to change anything, depending upon the model, anything that you change inside the gray will be immaterial to the outside world, right? So whatever happens, change within gray box. Change within the gray box. There is nothing that is going to replace. So the simplest way is, whenever you have a common source condition in this format, you can always replace with this circuit. Common source NMOS. Easiest way to replace without causing any difficulty, right? Every device you have to connect it the exact same way. Whatever happens is, when you have GMID or circuits, you can use. Whatever said and done, your small signal result will be the same. For example, if you have a resistor connected to the drain, you will connect it outside. If you have a resistor connected to the source, you will connect it outside. It should be identical, right? Follow this rule religiously or consistently, you will not have any difficulty in analyzing this work, right? If you trust the model, you will get the right answer. So you need to trust the process here and follow it. You will not miss out. So always trust the process that we are doing. Another thing is, you remember, always it is small signal. Do not add any other thing here unless it is informed or unless it is required. Do not insert anything, and sometimes you do not need to add also, because in your small signal analysis it is not needed. Remember, large signal will not be needed. Voltage sources, current sources are all large signal, so you can bring it out, either ground it or short or connect it to VDD, to the nearest AC ground. So that is your process that you will follow. Now, what happens in a real life example? So let us take an example. This is the easiest way to learn something that is there. Now, I think all the people might have come online by now. So I will now need volunteers who will tell me what are the inputs, what are the outputs, and how we will do a small signal analysis for the circuit which you are very familiar by now. Right? You have seen this circuit for the last 3 to 4 lectures, and you know what consistently works along. So you have a DC circuit here with 4 volts, AC circuit Vi of t. Okay, it is a time varying quantity. The output is drawn on the drain side. It is given as V out of t, again a time varying factor, where the DC signal is VDS, DCOP. Around it, there is a output signal that is coming here. Constant variance period of mu and Cox W by L is equal to K is given as 0.25 milliampere per volt square. Vt is equal to 2.0 volt. What is the RD that is given here? Constant companion 5 kilo ohm. The current flowing through this drain or through this resistor is given as small I capital D of t, time varying quantity, with I capital D plus I small d, again a time varying quantity. You now have the supply voltage given as 15 volt. Using 15 volt because it is a legacy design. Now this is a question. Perform small signal analysis. Perform small signal analysis and find voltage gain. What is the voltage gain? AV given as V0 of T divided by Vi of T. Right? So how do you begin this session? Let me turn on the video and start looking for people who are either paying attention or not paying attention to class. Right? Shrujan, can you come online and discuss what we take next? Shrujan, are you there?
Yes, sir.
Yes. Now please tell me, how do I proceed? First, I have to perform DC analysis. Clue number 1. So what happens there? What did I say? Whatever is your DC voltages, you first turn them off to 0. So this you make it
0.
off. Right? This
Yes.
is the only DC voltage, right? Then
Yes.
this is also off.
15.
No,
Yeah.
this is fixed, no? You don't turn it off, you keep it on only. So what is the resultant circuit? What is the resultant circuit? Can you turn on and video, draw it on a sheet of paper that is in front of you and show it on the video?
No, sir.
Why not?
Because I was not paying attention.
Wow. Wonderful. At least you're saying you're not paying attention. Okay. Pay attention next time. Dhanashri,
Sir,
if you have an answer, let's proceed. Step 1. DC
small
analysis.
signal.
Step 1 is always DCOP. Always DCOP. Forget, don't forget. DCOP, what do you get? So here is your VDS. This is your VGS. You have a fixed 4 volt here. This is grounded on the other side. 5K resistance, which is RD. Total ID current flowing through here. 15 volt supply. Okay, first assumption. First assumption is saturation. Let us enforce the conditions for saturation. What are they? ID is equal to K times VGS minus VT, the whole square. Now check, what is VGS? VGS, we definitely know is 4 volt, right? What is VT given in the previous diagram? How much is VT? VT is 2 volt. What is 2 volt then? 2.0 volt. So VGS is greater than VT. Good, right? So one condition is checked. Next, VDS needs to be greater than VGS minus VT. Do you know what is VDS value? Don't know. But we know what is current value. What is ID current? ID is K times. How much is K? What is K value? 0.25 milliampere. 0.25 milliampere. How much is VGS? 4 minus VT, 2 whole square. 0.25 milli multiplied by 2 square is 4. 0.25 into 4 is 1. So it is 1 milliampere. ID is 1 milliampere. So what is VDS? What is VDS value? 15 minus IDRD. That is 15 minus 1 milliampere times 5 kilo ohm. That is 15 minus 5, 10 volt. So VDS is 10 volt minus VGS minus VT, 4 minus 2. So this is also greater. So this condition is met. That means our saturation assumption is correct. So we now know that what is the VDS value, what is the ID value, what is the VGS value. We are good to go to the second step. What is second step? Step 2. Step 2, small signal parameter. What is the small signal parameter? Always GM and R0. All the others are given. So what is GM? What is GM? VGS minus VT. How much is that? 2 times K is 0.25 milli. VGS minus VT is 2. What does that become? 1 milliampere volt. Done. What is R0? R0 is equal to 1 over lambda ID. Right? We know there is no definition of lambda given. Since lambda is not given, let us assume that the value of lambda naught is 0. In that case, R0 becomes infinity.
Infinity.
What does that give information? That means it is open circuit. Right? R0 is an open circuit. You have identified. Now, what does that mean? How does your small signal equivalent look like now? Let us draw the gray box. Always remember, draw the gray box when you are working in the beginning. D, G, S. Next step, VGS. Next step, GM VGS. Next step, R0. In this case, R0 is an open circuit because it is infinity. Then this is your equivalent circuit of the transistor. Remember, VGS, GM VGS, R0. This is done. What are the other information? IG equal to 0. ID is given here. IS is given here, which is equal to ID. Now, what is the other element that you have missed? You have missed a resistive component. Where is the resistive component coming? At the drain connected to the DC source. DC source we will ground. So it will be drain to ground. Drain to ground. This is R. Right? Now this is your drain side. What happens on the gate side? On the gate side, if you remember, there is an input source, DC input source. That will come on the drain side. Gate side, sorry. Small signal Vi of t. This is source. Now what is pending? Pending is the output V naught of t. Right? Now this forms your small signal equation. What is the other thing? Source is connected to the ground. Gate is connected to the source. Drain is connected to the resistor and the output. So this is your small signal equivalent. What is this step? This step is your step 3. Step 3, replace the transistor with the small signal model. And step 4, add all the possible small signal voltage sources and other passive devices there. Step 3 and step 4 completed. So now these are the two information that you have. In this case, what happened? At the drain, we turned off one DC voltage source At the gate, we turned off another DC voltage source. So that's why they became short. And they shorted to the nearest node or to the ground. This one was to supply, which became the ground. This one was to Vi of t, so it connected to Vi of t. Understood? Next, Chanakya. You there? Sai Charan? Sai Charan or Charan Sai is one person who is always in class but never responds. First to class, typically. All the lectures, most of the days he is first, but I don't see him responding. I have to make him respond someday. Next, we will go up to step 5. Any volunteers for step 5? What is step 5? Step 5 is small signal analysis. How do we do that? Copy it. Copy the circuit. We will apply our very old, two very strong tools that we have learned from first year of engineering, or rather 3 tools. My most favorite tools. Tools for circuit analysis. What are they? Mr. Kirchhoff gave 2 of them. First one, Kirchhoff current law.
Yes.
Second, Kirchhoff voltage law. Third, and the most important one, which you have to never forget, superposition theorem. Never forget these 3. And one who is always there in the background but never in the foreground, Ohm's law. Okay. Later I will introduce to Murphy's law. For people who don't know, this will be your worst enemy depending upon the situation. So these are the 5 tools for any circuit analysis, and do not miss them. What are the straightforward information that we need for analysis? Here, first thing we need, you remember, I asked you remember 5 things. What are those 5 things you have to remember for circuit analysis? Can somebody quickly dictate them? VGS, VDS, IED, GM, or not. These are the 5 things that you need for analysis. Nobody is paying attention. Let me see. Looks like half the people are sleeping on the bed today, or had a nice lunch and not nice dinner and not responding. Either ways, let's proceed further. First, we understand what are the straightforward items that we have. We have VGS, VGS, straightforward Vi of t. Right? This is done. What is the next one? ID. Again, straightforward. ID is GM VGS. Done. What is GM value? 1 milliohm ampere per volt is what we find out, times VGS. So it will be VGS times whatever is the value. Next, what do we have? What do we have?
R naught is infinite.
R naught is infinite. Very good. Somebody is paying attention. Good job. Next, VGS over, ID over, R naught over, GM we have found out. What is next?
VDS is 10 volts.
V, capital
DS.
VS is 10 volt.
Yeah.
Correct?
Yes.
Remember, it is not, we need to find small VDS.
Small ds.
So what is that? You find out V naught. What we can do? We will apply Ohm's law there. What will you get? V naught is current through this resistor. And what is the GM VGS? Now, what is the current to the resistor? Whatever is going into ID is the same flowing into the R because it is outside. So what is that? V naught is equal to minus 5 ID. ID is defined in this direction. When it is going in the opposite direction, you will get a minus sign associated with that. So that is why this minus sign. What is 5? 5 is R, 5K. Right? So here, remember, there is multiplied by 1 milliohm. Here, this is multiplied by 5K. So 1K times is here, implicitly given. V naught equal to 5D. Now, what is ID? Right? What is the aim? You need to get, aim of this equation is to find AV equal to V naught by VI. Now, you need to combine these two equations. What are the two equations which have got V naught and VI? You have got VGS equal to VI is one equation, V naught equal to minus 5ID is another equation. So these two are the variables. So what is a relationship? You need to find out a relationship between VGS and ID. What is the relationship between VGS and ID? ID is equal to VGS times 1 milliohm. So when you replace minus 5 ID is VGS times 1 milli times 5K in 5 into 1 kilo ohm. So 1 milli, 1 kilo ohm will get cancelled. So V naught is equal to minus 5 VGS. Right? Now what is minus 5 VGS? Minus 5I. So now we have V naught and VI. So divide the equation by VI on both sides. So AV becomes V naught over VI equal to minus 5. So what this is? The small signal, okay, open circuit, right? It is a small signal. This is an open circuit. It is not a closed circuit gain. Open circuit gain of this amplifier is equal to minus 5. Okay. Let us see if we will try and increase the complexity of the circuit now a little more. Example 2. Okay, we'll add few more elements into our design. You will get note. I am giving you information. Gate question, exam question, assignment question. Pay attention. This can come in any or all or any two or any one of them. This will be a common feature. Let us draw the circuit now. Please pay close attention. The people who will help me respond this time are Geetika, Farah, Harshita, Kajal, Lasya Priya, Karthikey. Okay. I'm giving you the tough ones so that we will see if at least some people in the class help. Always note, I always start the drawing with the active device. This will help to even plan the small signal equivalent. Now you have this active device here. Let us start adding the passives. First passive is here. You have a capacitor. Then we have a small signal source at the input. Next, we touch the source. We have a resistance whose value is 2K. We have a resistor in parallel. Right? We will call this value as C. Gate done, source done. Next, coming to the drain. I have a 1K resistor here with a DC power supply of 10 volt. introducing a practical circuit. This is now going to be as practical as possible. Here we will understand many features. A resistor between the gate and the drain. Always note, this resistor will have a really high value. Why is that? What is the use? You will see the benefits of it. Now there is the capacitor again, value C. Bring it out. Add another resistor here, 3 kilo ohm. Here is your output defined as V0 of T across this resistor. Question. Perform small signal analysis. Perform small signal analysis. Find out voltage gain. Voltage gain defined as V0 by Vi AV. One information given to you, C is large. Okay, now let's begin the solution. Now, what are the important factors that we have? Lambda. How much is lambda? 0.005. Practical value, near to practical value. K. 0.4 milliampere per volt square. Another practical value, Vt. Now, this is not a practical value currently, right? Because our supply voltage is also very high. This is the question. Now let's begin. When we say begin, what is the first step? Answers to be coming from people.
You have to do the DC analysis.
You have to do the DC analysis. So how do I begin?
Vi of T is off.
Okay, I heard two people. I think the second one was Vani, if I'm correct. Trying to listen to understand your voices.
Yes.
Who was the first one? I'm still trying to map your name. Vani, you spoke both times or somebody else spoke before you?
Somebody else.
I spoke before Vani.
That
I was
is,
telling that it's
Geetika.
DC analysis.
Geetika, right?
Yes, sir.
Okay, good. I'm getting familiar with your voices. Faces, not much. Let's continue. First, DC analysis. Step 1. What happens in DC analysis?
Vi of T should be off.
Sorry? DC, correct. What all will be taken out?
Vi of
Okay, good. Control C, Control V. So in DC, all your AC will be turned off, right? This is equal to 0. Then, so this is shorted. What else? What else?
Assume saturation.
Even before that, okay, assume saturation, good. Who was this? Farah, right?
Yes, sir.
Yeah, assume saturation is good, but even before that, what are the other values that we can see? I did mention, right, passives, L and C. We said C is large. What happens when C is large? For DC, C becomes? What does it become? Remember, when DC, C becomes an open circuit. Right? Now, what happens in an open circuit? This is open. This is open. This is open. Right? So there is a break happening there. Right? Yes or no?
Yes, sir.
Yes. So how can you redraw the circuit? Now if you redraw the circuit, there is no line here. This is open. So this voltage is taken off. This is 0. This is 0. Now this is grounded. This is open. So this resistance is disconnected. So here it is grounded. This is open. So here this is open. It is only left here. So how does this circuit now look like? If you redraw the circuit, gate is grounded. Resistor is connected from gate to drain. 100K here, 1K here, 10 volt here, 2K here. Output, this is grounded. V0 is now ground. So what is the DC value? There is a current flowing here, ID. What is the DC analysis to be done? Simple. Start with what is known. What is VGS? How much is VGS? This is S. This is G. VG minus VS. How much is VG? VG is 0. Grounded. Right? VS. VS is the drop across this resistor. Minus ID times 2K. What is VDS? V minus VS. How much VDS? VDS, this node is connected to ground. But what it is? 10 minus 1K. 10 volt minus 1K times ID. VS is 2K times ID.
Sir, that is 100 volts, right?
Which is 100 volt?
VD.
How is it 100 volt?
In the above diagram, you mentioned it as 100 volts. No?
Sorry, this is 10.0 if you have not noticed. My mistake if it is not visible. 10, I'll write 10 volt, better than writing 10.0. This is 10 volt. Right? So this is 10 minus 3K ID. And VGS is minus 2K ID. Okay. What is VT? VT is 2 volt. Now, saturation. Conditions for saturation. Let's begin step by step. VGS greater than VT. In this case, minus 2K ID VGS is greater than 2 volt. So this is one equality. What will this happen? If you cancel 2 and 2 on both sides, minus KID is greater than 1, or ID, take the sign on the other side, inversion changes, equality changes, ID is 1 over K. Next, what is the other equation of inequality?
VDS is greater than VGS minus VT.
VGS minus VT. Now what will happen here? VDS 10 minus 3K ID greater than, how much is VGS? Minus 2K ID. How much is T? 2. Now we will do some rearrangement. minus 2 goes this side, becomes plus 2. So 10 plus 2, 12. Minus 3k ID goes this side, becomes plus 3k ID. 3k ID minus 2k ID is k ID. Now, in this case, 12 by k becomes is greater than ID. So now we have an equality. What is that? To be in saturation, ID has to be less than 12 by k or less than 1 by k. It should satisfy both the conditions to be in saturation. Now, we know the value of k, right? So what is the value of k here? How much is k? 0.4 milli.
0.4 milliamp.
K is 0.4 milliampere per volt square. What is 1 over 0.4 milli? How much is this?
Sir,
How much is this?
sir, here K is 1000, no, sir. For resistance, we have taken 1K and 2K.
May I know who spoke here?
Hello, sir.
Madam, flying factor.
Sir, you're not audible.
I am sorry. You are correct. I am absolutely. Am I not audible? Somebody caught my error correctly. So this is k. So it is 1 by 1000. This is 12 by 1000. So what is the condition here? This is what is the value? ID should be lower than 12 milliampere, comma 1 milliampere. So what is the lower among the two? This is one inequality that you have to check. With this, you find out what is now GM. Fill up the other equation. Now find out what are the other values. For VGS minus VT to be, ID has to be less than 1 milliampere. For saturation, this has to be less than 12 milliampere. To satisfy both conditions, the answer will be 1 milliampere. ID is 1 milliampere. Right? You replace what is VGS value minus 2k ID is minus 2 volt. K cancels out with M and becomes minus 2 volt. What is VDS? VDS becomes 10 minus 3k times 1 milliampere. 10 minus 3 volt is equal to 7 volt. So you found out what is VDS, you found out what is VGS, found out what is ID. Now let's validate. Is VGS greater than VT? VGS is not greater than VT. VGS is minus 2, VT is plus 2. So assumption of saturation is wrong. Okay. Now the next step, what you will do? Go back to the triode equation. Find out is VDS greater? Right? Is VDS greater? VDS is greater than VGS minus VT. VGS is minus 2, VT is minus 2. So VDS is definitely greater than minus 4. So what condition is this? VGS is less than VT, means it is cut off. VGS is less than VT is cut off. In cutoff region, what happens? Transistor is cut off. So whatever is the current that is flowing will flow through this resistor and go to the output. Right? All this, there is no current flow. So what is V naught of T? And since it's a DC, nothing gets blocked here. So whatever is the voltage, so the effective circuit now becomes K 10 volt. So this is your effective output. All the current flows through here. Since now the current, there is no route to flow. Small signal is grounded. There is no route to flow. Whatever is the output, you will get the inverse of it. So since the input is 0, the output will be same 10 volt that will be seen across this resistor, since there is no current flow. So your input is going to be 0, your output is going to be 10 volt. So very, very important to understand. So this can be an extremely practical circuit. Understood? How do you replace this value? Why this VGS became negative? VGS became negative because here there was 0 volt, here there was 2 volt. So the effective resistance became negative. What is the way to do it? This is called biasing a circuit. Right? Gate bias you will introduce. At this point, you will introduce a fixed DC bias value. You will introduce a resistor here R connected to ground. In that case, what will happen? There will be a DC current path. Follow the gray line or follow this yellow line. There will be a pink line better. There will be a DC current path to flow to ground. When there is DC current path, you will have a DC voltage applied here. Now, what is this DC voltage directly related to? The current flowing through this path. How much is the current? Current ID is, or the current I, which is going, it may not be ID, or you can call it as the bias current. Bias current is given as voltage from top to bottom, 10 minus 0, resistance along that path, 1K, 100K, R. So 101K plus R. Right? So what is the voltage value here? Voltage value will be voltage at the gate, VG, is I bias times R. Now, what is the condition? You want this value to turn on this device. This value has to be, VGS has to be greater than VT. VT value you know is 2 volt. Source value you know is 2 volt. So 2 plus 2 is already 4. So this potential voltage has to be greater than 4 volt. That is VG has to be greater than 4. Value if you fix here, VG is equal to 4. You know what is bias value. Find out what is R. Assuming the bias value is 1 milliampere. Right? You need 4 volt. What will be the answer? So 4 volt times something into R. What is the I bias? This I bias, R is 4 by I bias. So even if you want to get 4 volt, if your I bias is 1 milliampere, your R will become 4K. So 4K, 101K plus 4K is approximately very similar to 101K. So for all practical purposes, you can find out the current to be, what will be the current value? 10 divided by 101K. That is 0.1 milliampere approximately for practical purposes. So now your R will be given as 4 divided by 0.1 milli. How much is that? That will be equal to 40 kilo ohm. So when R equal to 40K, you are just in VGS minus VGS equal to VT, right? The total value that will be here, 4 minus 2 equal to 2, VT is equal to 2. So you will be in the edge of threshold. Any value greater than 40K is only going. Now what will happen? If you put 40K, what is this value now going to change as? 10 divided by 140K. This will be the new value. What is the total current? 1 by 14K. So this will be 0.07 or 0.8, around that value. So that will be the total amount of current. And now that if you do iteratively, you will find that once this amount of current flows, this resistance is again insufficient. So you will straight away try and add a little higher value and decide what is the amount of overdrive that you need. You remember we said about what is overdrive. Remember, this is how you have not even done AC analysis still. You are still in DC. You need to find the DC operating point here. So this is going to be as practical. In this particular case, if you want an overdrive, that is VGS minus VT of 0.1 volt equal to 100 millivolt, then what will happen? VGS minus VT equal to 0.1 or VGS equal to 2.1 when VT is 2. Now VGS is VG minus VS. We know that VS is already 2 volt. So VG will become, how much will VG? VGS plus VG. This will be 4.1 volt. Now, if you need 4.1 volt in that resistive divider, where this is 101K, 100 plus 1, 10 volt, this is R. You know that this voltage is 4.1 volt. Now, what will be the current flowing here? Iterative process. Your ID will be 10 minus 4.1 divided by 101K, because it's current through this resistor. Yes or no? No. 101K plus R. Total divided by this. So how much is this value? 5.9 divided by 101K plus R equal to ID. But what is the voltage drop that you know here? This is 5.9, right? So the current flowing through this one has a drop of 5.9 volt against 101K. So voltage, Ohm's law. R is 101K. Voltage is 5.9 volt. What is I? So your I gives, how much is I? 5.9 volt divided by 101K. How much is that current value? K becomes milli, 100 becomes 0.01 milli multiplied by 5.9 approximately. So multiply by, bring the two zeros here, 0.059 milliampere, or for all practical purpose, it is 60 microampere. So now your ID becomes 60 microampere, or IG, not ID. Now that you have found IG, you can find out what is the value of R. R is equal to 4.1 volt divided by 60 microampere. How much is that? 4.1 by 60 times 1 mega ohm. So 4 by 6 approximate. 4 goes 1 times, 4 1 over 15 times. 1 over 15 into 1 mega ohm. How much does this value become? .2 by 3. Correct? No. This is the easier way without using calculator. How do you approximate? 1 by 15. Okay, 10 by 15 is 2 by 3. So 2 by 3 is 0.666. Now since it is 2 by 3, we have to do 0.2 by 3. So this decimal will jump here. So it becomes 0.067 times 1 mega ohm. If you multiply, this is 67 kilo ohm. So R equal to 67 kilo ohm. In the previous approximation, we found this to be 40K. And if you look at the current approximation, 1 over 15K we get. Approximated, we said 0.07 milliampere, 70 microampere. With a very close approximation, we got the value to be 60 microampere. So now you have finished the DC bias. You have found out that you can bias the circuit in this manner. $67K, 100K, 1K. Here, if you apply a DC bias and apply the voltage input here, now you can perform the analysis with lot more simplicity. Right? This is one of the most common amplifiers with positive feedback. See, there is some positive feedback. Here you will get DC bias voltage, biasing current, or a DC path for current to flow. Right. So we will next do, I will ask you to complete this and send it by email if possible. Complete the AC analysis, find out what is the gain. But the answer actually is done. It is a inverter, or so there is very, very high gain. Right? With this, we will move in the next class. We will begin single stage amplifiers. Right? Where we will learn about common source, common gate, and common drain amplifier topologies, single stage. Right? Once we do this, you will understand many, many more new applications here. We will understand what are the ways connections have been done. The simplest way, we will understand what are the current amplification we can do, how we can do voltage amplification, and how we can do no amplification. It will just be a buffer, voltage buffer, pass through, right? Or an impedance transformation, so you can call it. We will also understand this first step. Each of these becomes a first topology for all your advanced circuits, right? Here comes your first project where you are going to study of differential pair. In 2 classes from now, you will get introduced to differential pair using one of these. So all the people who are doing the first project, you can ideally begin your work here. Second, people who want to do RF signal analysis, you will understand that common gate based low noise amplifier. Pay attention when we are doing common gate. Third, people who are going to do delay cell or ring oscillator, pay attention here. You will be using common source based amplifier or a delay cell. Next clue classes are extremely important for analog design. Do not miss, and please pay a lot of attention to them. Your next class will be on Saturday, and we will close the class here for today. Any questions? Any questions? If not, please turn on your videos for the customary photograph. Saturday will be a crucial class, okay? Before we start our lab sessions. So please do not miss Saturday's class, no matter what, okay? As usual, all the regular people are on video, all the not regular people are not on video. Thank you. Has everybody's photograph come? No, today everybody is a little dull. From here on, we will go into our serious designs going forward.